In the last episode, when we took apart what a large language model really is, we kept calling it a next word predictor. That was a small, useful lie. A model does not actually predict the next word. It predicts the next token. And almost everything strange about how these systems behave, the way they fumble simple spelling, the reason your bill is what it is, the reason a sentence in Hindi can cost far more than the same sentence in English, all of it traces back to this one quiet step that happens before the model even starts to think. So let us start where the model itself starts, with tokenization. Quick note before we dig in. If you find this useful, subscribe and drop a topic you want explained in the comments. Now let us get into it. Here's the whole idea in one sentence. Tokenization is the step where the model chops your text into small chunks called tokens and turns each chunk into a number, because a language model cannot read letters at all. It only does math on numbers. So before a single word of your prompt reaches the model, it has to be cut into pieces and converted into a list of numbers the machine can actually work with. The model lives its entire life in that world of numbers. It never once sees the letters you typed. Now you might assume a token is just a word. Sometimes it is. But more often, a token is a piece of a word, a common chunk of letters that shows up again and again across billions of sentences. A rough rule of thumb that the major labs themselves use is that one token is about 4 characters of English, which works out to roughly 3/4 of a word. So 100 words of typical English is around 130 tokens. Short common words like the, and is each become a single token. But a longer or rarer word gets split. Take the word tokenization itself. To you, it is one word. To the model, it might arrive as 3 separate tokens, something like token plus is plus action. The model never sees the whole word. It sees 3 numbered fragments and learns how they tend to fit together. So how does the model decide where to cut? It is not random, and it is not a dictionary someone typed by hand. It is learned from data using an algorithm most of the big models share called byte-pair encoding. The idea is beautifully simple. You start by treating every single character as its own token. Then you scan a giant pile of text and find the pair of tokens that sit next to each other most often. Maybe it is the letter T followed by the letter H. You merge that pair into a new single token, TH. Then you scan again, find the next most common pair, and merge that. You repeat this tens of thousands of times. The result is a vocabulary where the most common chunks of language, whole frequent words, and useful word parts each get their own token, while rare words quietly fall back to smaller pieces. The model behind GPT uses a tokenizer of this kind with a vocabulary of around 200,000 tokens. Llama and Claude use their own tokenizers built on the same family of ideas. Each model has its own, which is why the exact same sentence can be a slightly different number of tokens depending on which model you send it to. Now, here is the part that makes the whole abstract idea click, and it is a mistake you have probably seen with your own eyes. Ask a model to count the number of times the letter R appears in the word strawberry, and for a long time, the best models in the world would confidently tell you 2. The real answer is 3. People took this as proof the AI was dumb. It is not dumb. It is blind to letters. To the model, strawberry is not a string of 10 letters it can count through. It is maybe 2 or 3 tokens, straw and berry, say each just a number. Asking it to count the R's is like asking you to count the letters in a word written in a language you have never seen, where you only recognize whole shapes, not the strokes inside them. The information was destroyed before the model ever got it. Once you understand tokenization, this stops being a mystery and becomes completely predictable. That same blindness explains a lot of small quirks. Why models can be shaky at arithmetic with long numbers, because a number like 123,456 might get chopped into odd token chunks that do not line up with the actual digits. Why they sometimes stumble on rhymes or wordplay. Why they handle a typo strangely, because one misplaced letter can shatter a familiar single token into several unfamiliar fragments. None of this is the model being unintelligent. It is the model working with the only thing it was ever given: tokens. Now let us talk about the part that hits your wallet, because this is where tokenization stops being a curiosity and starts being money. When you use a model through its programming interface, you do not pay per question. You pay per token. Both the tokens you send in and the tokens it generates back. Prices are quoted as some number of dollars per million tokens. So tokens are quite literally the currency of artificial intelligence. Let me make it concrete. Say you paste a 10,000-word report and ask for a summary. That input alone is roughly 13,000 tokens. If the model then writes you a 500-word summary, that is about another 650 tokens going out. You are billed for both halves. Now, imagine you are not doing this once, but 10,000 times a day inside a product. Suddenly, the difference between a prompt that is 2,000 tokens and one that is 4,000 tokens is not a rounding error. It is the difference between a business that makes money and one that does not. Tokens also shape speed, not just cost. A model generates its answer one token at a time, each new token built on all the ones before it. So, a longer answer literally takes longer to produce, and a longer prompt takes longer to read in. When people complain that a model feels slow, very often the real culprit is simply that a huge number of tokens are moving through it. Fewer tokens means faster and cheaper, almost always. This is the first real lever you have as a builder, and we will keep coming back to it. Now, here's the part that is genuinely unfair, and most people never notice it. Tokenization is biased toward English. These tokenizers were trained on text that was overwhelmingly English, so English gets the efficient, short tokens. Other languages do not. The exact same sentence with the exact same meaning can take 2 or even 3 times as many tokens in Hindi, Arabic, Thai, or Burmese as it does in English. And remember, you pay per token, and you are limited by tokens. So a speaker of one of those languages pays more for the identical request, gets answers more slowly, and runs out of room in the model faster. A language written in a non-Latin script can have nearly every character split into multiple tokens. This is a real, measurable inequality baked right into the plumbing, and it is one of the quiet reasons multilingual quality and cost are still such an active problem. When a lab releases a new model and boasts about better multilingual support, a big part of what they have actually improved is the tokenizer. So how does this land differently depending on who you are? As an individual, you mostly feel tokenization through limits and through letter games gone wrong, but you can see it directly. The makers of these models publish free tokenizer tools on the web, where you can paste any text and watch it get split into colored tokens in real time. Do that once with an English paragraph and then the same paragraph in another language, and you will never forget the difference. As a startup building on top of a model, tokenization is something you actively manage. You trim system prompts, you cut needless words, you choose a model whose pricing and tokenizer fit your traffic, because at scale, every token is multiplied by millions of calls and lands straight on your cloud bill. And as a large enterprise, tokenization becomes a budgeting and fairness question. You forecast spend in tokens across whole departments, and if you serve customers in many countries, you have to account for the fact that your non-English markets quietly cost you more per request for the very same feature. So let us bring it home. Before a model reasons about anything, it cuts your text into tokens and turns them into numbers, using a vocabulary it learned by merging the most common chunks of language. Those tokens are why it cannot count the letters in strawberry, why your bill reads the way it does, why long answers feel slow, and why other languages cost more. Tokens are the atoms of everything that follows in this series. But notice what we still have. Just numbers standing in for chunks of text. The model does not yet know that the token for king and the token for queen have anything to do with each other. So how does a machine get from a meaningless ID number to something that actually captures meaning, that knows king and queen are related, that Paris is to France, as Tokyo is to Japan? That is the leap we make in the next episode, when we turn tokens into vectors and watch a computer start to understand meaning. That is the core of it. If this helped, hit like and subscribe, ring the bell for the next deep dive, and tell me in the comments what you want broken down next. Thanks for watching.